Welcome to this video on transforming to linearity. This concept involves taking a linear regression and analysing it both in terms of the correlation coefficient and the residual graph to determine whether or not data is in fact linear or needs to be transformed to some other mathematical model. So let's have a look at our example. So the question we have today, the area in kilometres squared of several towns/suburbs and the corresponding population of these towns and suburbs is shown in the table to the left. Okay, so this is all pretty self-explanatory. The area in kilometres squared and the population in thousands of people. So first of all, our first task, determine if the association between population and area is linear. So for this, we'll turn to the TI Inspire CX CAS calculator to make our calculations. We have our data already populated here for the area and population. So it's the data we started with, the area in kilometres squared and the population in thousands. So first of all, let's perform a linear regression. Menu, stats calculation, and linear regression, y equals a plus bx. Now we have to inform the program that the x was the area and the y was the population. And that returns our information here. So we can see the y-intercept for the equation, the gradient, the coefficient of determination, and the correlation coefficient, plus all the residuals if we're interested as well. Not the highest correlation, 0.78 coefficient. So let's now let's have a look at this visually, see what we've got. This time we'll go to a graph, and we wanted population against area. Okay, now looking at this, this does not fit a linear trend at all. Whilst the correlation coefficient is relatively high, the graph we have looks nothing like a linear relationship. As always, we can plot a regression line to any data. It will simply create a line of best fit. And there we have it. Line goes straight through, and here's our equation. Population equals 2.02 plus 0.000288 times the area. But clearly that is not really a straight line relationship. Now, to confirm that, we'll hit the menu, analyze, look at residuals, and we'll do a residual plot as well. Clearly we see here the residual starts large negative, goes into the positives, and then back down to a negative, what I'd call a classical frowny face. So we probably are looking at some kind of transformation of this data being required. Okay, to summarize our findings between the population and area, let's have a look. First of all, the linear regression summary gives us a correlation coefficient of 0.78, which is generally strong and positive. Scatter plot probably shows a relationship that doesn't look linear. So our findings so far, the linear regression of population in thousands is equal to 2.02 plus 0.000282 times the area in kilometres squared. It has a correlation coefficient of 0.78, which indicates a pretty strong and positive association. However, when we look at this residual plot, we find there is a curve, what I'd call a frown curve, starting at negative residuals, moving into positive, and then back to negative. The original data probably has a non-linear relationship, so we need to consider transformations. The skill is working out which transformation to undertake. So here we have what we call the circular transformations that allows us to select the correct transformation options. So we have here our circular transformation, and we also have our original data. Now if I look at this, you can see how the curve bends from bottom left to top right with a green line. Which of these four quadrants have a similar shape of curving from bottom left to top right? It's this one here. It curves bottom left to top right. So we can ignore the other three transformation quadrants. Here we've got three transformations available to us. So we can use this to, first of all, investigate what happens if we square the y-axis variable. What happens if we take the log of the x value? And also the reciprocal, or the inverse of the x. So we've got three transformations to consider to see if we can find linearity. So first of all, the y squared transformation. So the y variable was population. So if we square that, this is our new data we've set. Let's now again use our TI Inspire to analyze the variables. Let's now examine a y-squared transformation. So the y variable was the population. So let's make a heading and we'll call it pop squared. Okay, instead of doing every piece of data individually, let's put this in. So pop squared is equal to, I just type the equals button and it comes up with pop squared, is equal to pop. So that's the column here. It's identified as a capital. So we know that that's this column here, column B for population, and we're going to square it. Okay, so when we take our value 1, we square it, we get 1. 1.5 squared is 2.25. So we've now filled in our pop squared. Okay, so this is our first transformation we're investigating. Let's have a look at a regression of this data. So stats calculation, y equals a plus bx. Our x values were our area, and our y value, importantly, is no longer population, but pop squared. Okay, so here's our information. So using a y transformation, our variable population, if we square it, we end up with now a y-intercept of 4.45, a gradient of 0.001587, a coefficient of determination, and the correlation coefficient of 0.86. Okay, that information tells us we've improved our original R value here. Our correlation coefficient is improved. That gives us some hope, but we may have found a better transformation. But to work this out, let's do a visual. We're going to plot. This time it's going to be the pop squared, not the pop. We've transformed the y squared. And on the horizontal we have area. Again, this doesn't look very promising, not linear at all. Let's analyze and complete a regression. There we go, here's our equation. Unfortunately, that doesn't fit the data well at all. And we can confirm that by analyzing a residual plot. Once again, we have this negative residuals to positive residuals back down to negative, what I call a frowny face. Okay, and so this kind of indicates we are probably looking at further transformation. This transformation has not linearized the data whatsoever. So we've done our transformation. Let's have a look at the summary now in terms of the association between population squared and area. So first of all, our R squared has improved somewhat. Our scatter plot, however, still doesn't look linear. So from those two findings, we say this particular linear regression states population. Now, we transform the population, the y variable, to population squared. So when we write this linear regression, the population is actually population squared. The TI Inspire won't change that. They'll just say a y and an x, but we have to remember what this y represents. Is the regression line is population squared equals 4.46 plus 0.00159 times the area in kilometers squared. It has a correlation of 0.86, which indicates a strong and positive association. Now these dots all follow a pretty similar pattern and hence the high correlation. However, clearly this is not linear. Let's look at the residuals. Our residual plot shows a curved pattern from negative residuals to positive to negative, what I call a frowny face. The original data probably has a non-linear relationship. This has not been a successful transformation. We have to look for an alternative transformation. So we've given up on the y squared, that's not possible. Our second option from our circular transformation is the log of x. So we now take an area and we take log to the base 10 and we get these numbers. Let's put these values into the TI Inspire CXCAS calculator and analyze the association between the variables. Let's analyze our second transformation. This time we're looking at log to the base 10 of the x variable. So our x variable was area. So we'll give it the heading log area. Okay, let's fill in the data. Equals, and we want to take a log. So it's control or second function of 10 to the power of x. There's our log. We need to explain it's a base 10 calculation. And we are taking the log of our column labeled area, and it goes bold when we type that in. Okay, now that's not in decimal mode, so let's see if we can fix that up. So let's go back to our menu, our home, and settings, document settings, calculation mode. Instead of auto, let's go approximate. Press OK. We're going to open up some page to get back in. There we go. All our logs are now in decimals. So let's now perform a linear regression, so stats calculation, linear regression, y equals a plus bx. Now our x here, not area, we're taking the log of the area. That's the transformation we're applying, and population is our y. So here's our information. We find the y-intercept for this particular function is 0.0323. The gradient is 0.9898. The r squared, the coefficient of determination, is 0.999. That's extremely high. And the correlation coefficient is 0.99999. This is looking very promising in terms of linearity. They're extremely high numbers. We can't be sure until we have a look at our graph. So we're looking at population on our y-axis. We are looking at the log of area on our x-axis. That looks very promising indeed, nice and linear. Menu, analyze, regression. Let's put in our equation. Here we have a beautiful straight line with a very, very high correlation coefficient, as seen earlier, and an equation that fits a nice linear. Finally, let's check our residual plot. This will be the telling factor. Residuals, residual plot. Okay, here we have a residual plot with our residuals being scattered around the x-axis. So it's positive, negative, positive, positive, negative, positive. It's all over the place. This is good, this is perfect. So at the end of this particular transformation, we find the points of the residual are randomly scattered above and below the x-axis, and this original data probably had a linear relationship. Our findings now about the association between population squared and area are as follows. First of all, we have an R value of 0.9999, exceptionally high. Our scatter plot is very encouraging, a straight line relationship. So our findings so far, the linear regression is population is equal to 0.0323 plus 0.990 times not x, but the log of the area. This generates a correlation coefficient of 1, which indicates a strong, in fact nearly perfect, positive association. And the graph visualizes that it's linear as well. But always we must check our residual plot. Our residual, which is pleasing to see, has scattered from positive to negative, positive to negative. The points of the residual are randomly scattered above and below the x-axis. The original data probably have a linear relationship. Finally, we've got our third and final transformation, which is our inverse or our reciprocal x data. Let's see what it finds. So we're taking the reciprocal of x, which is the area, 1 on the area. Let's enter our data into the TI Inspire CXCAS calculator to analyze the association between the variables. Let's look at our final transformation, that being the 1 on x transformation, the reciprocal of x, or in this case, 1 on area. So I'll call it recip area. So it makes sense to me, recip area. Now, equals, it's simply 1 divided by area. So it's 1 on area. Okay, it becomes bold, it recognizes as a heading. Okay, so 1 divided by 9 will give us 0.1111. 1 divided by 32, 0.0325, etc. Okay, so there's our data. Let's see how this one stacks up or compares. Statistics, menu stats, stats calculation, linear regression, a plus bx. Now in terms of the x, we've transformed the x, we're using the reciprocal of area, and the y stays as normal population. You can see here, here's our y-intercept, 2.845. Here's our gradient, minus 19.98. Our coefficient of determination is 0.55. Our correlation coefficient is minus 0.742, the lowest of all, plus that's negative now. So that doesn't hold too much promise, but again, as always, let's check the visual as well. So we're going to graph this time our population on the y-axis against our 1 on area or our reciprocal area on the x-axis. That does not look linear at all. Let's add in our regression line. Because we can always fit a regression line, it simply finds this middle point using the least squares technique, but that doesn't fit that data whatsoever. And finally, let's have a look at our residual plot. As you can see here, a residual starts off with quite a large positive residual, getting smaller, so positive, then several negative residuals, back to a positive residual. This does not indicate a linear relationship at all. So this original data probably has a non-linear relationship. This isn't the transformation to linearity. Our findings are summary, looking at the association between population and the reciprocal of area. So R, our correlation coefficient, is now negative 0.74, one of the lowest values we've found so far. That doesn't give us much encouragement. Our graph, unfortunately, does not fit that line very well. Okay, this is not a linear association. So the linear regression we have here is population is equal to 2.85. Take 20 times the reciprocal of the area. Again, the x value here is a reciprocal. That's our transform data, so we must write it as 1 on area. As I said earlier, we can find a linear regression line, least squares regression line for any set of data. However, this clearly is not a linear association. Our residual plot indicates this as well. The residual plot shows a curved pattern with a series of positive to negative and then positive residuals along the x-axis. So the original data probably have a non-linear relationship. Transformation of this data may be required. So the one we've left with, y squared didn't work, the reciprocal of x didn't work, however the log to the base 10 of x gave us an excellent outcome. So here's all our information, our original data, our y transformation, our log 10 of x transformation, and our reciprocal x transformation. You can see our original data was not linear, had an R value, correlation coefficient of 0.78. Our second transformation, the y squared transformation, improved that to 0.86. However, the residual is still a frowny face. So the findings, this is not linear. Our log 10 x gave a correlation of 1. The residual is scattered, so that was linear. Our reciprocal of x transformation gave the lowest of all R values, correlation coefficient values. It gave a residual with a smiley face and wasn't linear. So our log to the base 10 of the x transformation is in fact our correct mathematical model. So the original data is best represented by the following mathematical model. Population in thousands is equal to 0.032 plus 0.990 multiplied by the log 10 of area in kilometers squared. Now we have this, let's look at a couple of applications. We can now use this formula, or equation rather, to make predictions. So example 1, use the above equation to predict the population of a suburb of area 500 kilometers squared. So our data is population equals question mark, area equals 500 kilometers squared. And here's our equation. Let's sub in the area of 500 kilometers squared. It's in the same units, so we sub that straight in. Then if we take the log to the base 10 of 500 times it by 0.99 and add 0.0323, we find the population for a suburb of area 500 kilometers squared is 2.7, and that is in thousands. So it's 2,700 people. Our second and final example, use the above equation to predict the suburb area in kilometers squared, given a population of 4,000 people. So the area is question this time, it's the question mark. Population is 4,000 people. Now this equation uses population in thousands, so I'm writing this as 4,000 people. Let's sub the 4 in. So 4 is equal to 0.0323 plus 0.990 multiplied by the log base 10 of the area in kilometers squared. A bit complicated to solve this one using transposing techniques. So we'll just use the solve function of the CAS calculator, where we write solve, open brackets, the equation, comma, the variable we're trying to solve, the unknown x, close brackets. And that tells me that if I had a population of 4,000 people, this equation predicts the suburb area would be 10,180.7 kilometers squared. Look, thank you as always for watching this video. I hope this helped explain some aspects of transforming to linearity. Of course, if you've liked this, please give it a like, share and comment, and I'd love you to subscribe. Again, thanks for watching.